Good evening. Once again, I'm Mr. Steele. I'm here to work through another one of the videos, helping you work through the Essential Skills Quiz model for the first half of Honors Pre-Calculus. In this video, we're going to be focusing on the fourth question, which is centered on the skill involving both factoring and, of course, solving. So as the video is titled, you're going to be factoring to solve, using factoring strategies to break apart a polynomial of some kind, and then solving the resulting equation so that it satisfies the fundamental theorem of algebra. In this video, I'm going to start by overviewing the techniques. I'm not going to go into too much detailed depth, just to kind of make sure you remember sort of the usual suspects, the ones you're going to potentially run into here. And then I'll work through, I believe there are 4, possibly 5 examples illustrating those techniques. So rather than beat around the bush, let's just dive right in. Let's get into instead of beat around the bush, let's jump right into the weeds. It's a lot of agriculture puns now that I think about it, but yeah, here we go. So, as I mentioned, I want to start with just some key ideas, and in this video, key ideas really just refers to the factoring strategies that are out there. We are going to be solving polynomial equations in this video, and in the fourth question on the ESQ, but in this case, we really are just talking about the factoring strategies because the solving part will always be kind of the same thing. Set things equal to 0, solve for the missing variable. So in order to break apart these polynomials so we can do that straightforward and familiar solving approach using the zero product property, we need to kind of be reminded of what the GCF, what the techniques are for factoring, starting with the simplest of the ones up here, the GCF. So just kind of a reminder, GCF, it doesn't matter what form you start with, it doesn't matter how many terms you have. GCF is all about whether or not those terms share some common factor, like GCF stands for greatest common factor. So it can be a really simple expression as much as something like, I don't know, this. So if you were asked to factor this, you could do so by recognizing that there are 3 x's in each of these. There's an x to the third basically in each of them. You could pull out that GCF of x to the third, and then you'd be left with x minus 9 left over. So that is using the GCF factoring method because x cubed was the GCF. So this is something you'll have to do before potentially using other factoring techniques, particularly if it's a trinomial. There could still be something hiding underneath, but there is the GCF technique. It's something to be on the lookout for every single problem you run into. The next one is, and let me add in here really fast before I do, any number of terms is possible for you to use a GCF. I mean, I suppose it'd be odd to try to have one for a single term, but everything else is good to go. So the second option, grouping. Grouping for us is typically going to be 4 terms. So you're going to recognize it by finding it in the 4-term polynomial. And as far as what we usually have, you'll see some familiar stuff. You'll have something like x cubed minus x squared. Then let's go minus x plus 1. So let me see if I got that right. Yeah, there we go. So in this case, when you group, it's that strategy. And again, there's a bunch of different ways to do this, including the box and other things. But for me, I've always used this split the middle method, and then I look at each one and factor out a GCF. That gets me x squared times x minus 1. On this next one, we can pull out a negative 1, and we'll be left with x minus 1. Then notice we have a GCF of x minus 1, so we can pull that out in front. And then we're left with this. And of course, there's more factoring to be done here, but you get the idea. Basically, 4 terms, and there's a shared GCF between the first 2 and the last 2. That's when we can use the grouping strategy or factoring by grouping. For the hard diamond, we've already covered that in a previous video in this ESQ model series, so I'm not going to go into as much depth, but basically the diamond or hard diamond, both of them are possible, or they're consideration when looking at a trinomial. So the classic ax squared plus bx plus c. If the problem is a hard diamond, that means this leading coefficient a does not equal plus or minus 1. If we have just a classic diamond, in that case, that's when a equals positive 1 specifically. If it's negative 1, you can treat it as a GCF, but basically we've done this one before. You kind of know the trick. What 2 numbers multiply to a times c? And multiply to positive b. It's that same game you've been doing for a while. The fourth one down there, also one that we've run into multiple times. In fact, there's a difference of squares right here. This is specifically when you have 2 terms. So if you have 2 terms and they fit a particular pattern, you've got a difference of squares possibility. So for instance, if I had, I don't know, x to the 10th minus 25, like of course there's probably lots of factoring that can happen here, but this would be considered a difference of squares because each of these is something squared. This is x to the 5th squared minus 5 squared, oops, so 5 again, which means you can write it as x to the 5th plus 5 times x to the 5th minus 5. And so this piece, while there's again more that we could do out there, this two-term polynomial does factor into something plus, something minus, a really familiar structure. And by the way, I should have noted on the previous one for diamond work that this is specific to 3 terms. And then last but not least on this page, and I will admit that I'm actually pretty happy with the organization that I ran into here. Oh, there's 2 more on the page. I forgot I included that one. We've got the fake quadratic. I should note that that's typically going to be a 3-term polynomial. And basically a fake quadratic is one that looks like quadratic, but it's not second degree. So the easiest one that I can think of to sort of represent this would be x to the 4th minus 7x squared plus 12. This looks just like a diamond problem, and in fact you can sort of factor it as a diamond problem and quickly get -3 and -4. But because the powers here are 4 and 2, this doesn't factor into x minus 3, x minus 4. It factors into x squared minus 3 times x squared minus 4. And now from here you would have to continue your work in order to factor it completely, because those are both differences of squares. But basically this is where you treat something that looks like a quadratic or a diamond problem like a diamond problem, but you make sure to adjust the degree for what's inside the problem. And then last but not least on this page, I didn't see any examples that featured this particular technique in the ESQ model, but that doesn't mean it couldn't possibly show up somewhere else. So let me just remind you about MOP. MOP is specifically for 2-term polynomials, but they're 2 terms where a particular structure happens. It's where you can rewrite or begin something a cubed plus b cubed, where this can be written as something cubed plus or minus something cubed. And the strategy here, which again, if it shows up, cool. If it doesn't, it doesn't. But if you have a cubed plus b cubed, actually do it as plus or minus b cubed, you'll get a plus or minus b. So you get a binomial in here, a linear factor. Then a squared, ab, and b squared. And then for your signs, it's matching. So it matches the original sign. Then it's opposite, and then it's positive. So for the opposite, we would have minus plus, the opposite of whatever we had first. And then the last one is positive regardless. And so basically this is something that I think is going to be pretty rare on our ESQ here, but is definitely a strategy that can show up in the future in various places. Some are difference of cubes, also known as MOP, matching opposite positive. So with that quick overview under our belts, let's dive in and do a couple problems here. Let's see these techniques used in action. So we're going to start with problem number 1 from this question type, where we are instructed to solve the polynomial equation by factoring. And this one gives us x to the 4th plus x squared minus 20. So I've already listed the strategy off to the side, but we can talk about why it is that I'm seeing a fake quadratic. And there's specifically a couple reasons for why. The first one is, of course, that I see 3 terms. And when I see 3 terms, that makes me think of sort of the classic quadratic trinomial, the parabola equation that we're so used to. So basically that's my first little clue that's present. The second thing though is that I know this isn't a diamond 1 because our degree here is not equal to 2. If it was degree 2, it would just be a quadratic polynomial. We'd have all those nice factoring techniques ready to go. This one is degree 4 because the highest single degree in here is 4. Therefore, we do not have the ability to just straight up use diamond. We're going to have to do some extra work afterwards. Having said that, though, we can kick this off by using the diamond. Because it's got 3 terms, it looks like it should meet it. So we're looking for what 2 numbers multiply to -20 and add up to +1. And, with a little bit of thinking, I'm sure you'll arrive at +5 and then, -4. So there's our stuff. Now, when we go to break this up, we have to be careful. So in case you're less certain where it came from in my little previous example, what you can do is you can think about it as this being our way to split up that central term. Instead of writing it as +1x squared, we're going to write it as +5x squared. And then -4x squared, which just breaks it apart. It just separates it, that +1x squared, into 2 pieces. And then, of course, we still end with that same constant. From here, I can treat it as a grouping problem if you're not at all certain. So I can treat each one as kind of separate. I almost feel like I'd rather do it that way. Treat each one as a separate piece. This will be x squared times x squared plus 5. On this left or right side, we'll have negative 4 times x squared plus 5. All of that is then equal to 0. And now we have a GCF of x squared plus 5. So I'll GCF it out and be left here. X squared plus 5 times x squared minus 4 equals 0. So good stuff overall, but obviously we can go a little bit further. X squared minus 4 factors into x plus 2 times x minus 2 using a difference of squares. And actually x squared plus 5, it might not necessarily jump out at you as being an obvious difference of squares, particularly because it's not a difference. But x squared plus 5 is the exact same thing as x squared minus a negative 5. And if we treat that as a difference of squares, weird as that is, we'll get one factor plus, one factor minus. Each one will have an x owing to that x squared. And then on that last little piece over here, we'll get the square root of negative 5. And now that looks pretty wonky and kind of weird, so let's just write it like it should be. This will be x plus I root 5 times x minus I root 5. And from there, we've got our last two factors. Now, having said that, it's tempting to leave the problem right at that point and just say, okay, cool, got it, I am finished, everything is complete. But remember, our problem originally wasn't asking us just to factor it. It was asking us to solve the equation. So our answer needs to read x equals in order for that to be true. Well, in our case, each of these possibilities can be set equal to 0. Like each one's zeroness, zeroed out quality, is a potential possibility here. This is the zero products property in action. One of these numbers has to equal 0 for their product to be 0. Therefore, we can just figure out what makes each one 0 and we'll be finished really fast. X equals negative 2, x equals 2, x equals negative I root 5, and x equals positive I root 5. And if you're wondering why I didn't just use plus or minuses, there's nothing necessarily wrong with that. I just like being able to very quickly and visually confirm that we have the correct number of solutions. The fundamental theorem of algebra says the number of solutions up to multiplicity should match the degree. I see 1, 2, 3, 4 distinct unique solutions. And I see up here we had a degree 4 polynomial. That's a good sign. It looks like everything's working the way it's supposed to. Question number 2 immediately sort of pushes us into a narrow set of possibilities. Our polynomial in question only has 2 terms, which means it's either a sum or difference of cubes or a difference of squares. And in this case, because our powers in both cases are even, this looks like it's going to be a difference of squares. So that's the way I'm going to think about x to the 4th minus 81 equals 0 is as a difference of squares problem for us to tackle and solve. So in here, in order to think of things as a difference of squares, the idea is, like I mentioned this briefly earlier, but the idea is if you have a squared minus b squared, then that will factor into the product of 2 distinct factors, a plus b and a minus b. And that product will give you a squared minus b squared. And as a heads up, if you're wondering where the middle term goes, that gives us negative ab, and this gives us positive ab, so they zero each other out. They, quote, cancel one another out. So with that said, a good way to look at this is to try to figure out what's being squared here, because those a's and b's come from whatever was being squared in the difference of squares. So in this case, I'm thinking, what squared minus what squared is it that we are looking at and inspecting here? And pretty obviously, the 81 is just 9 squared, so we'll pop a 9 in there. But for x to the 4th, we got to think for a second to realize that, hey, that's just x squared squared. And what that means is we can then factor this into the product of 2 factors. The first factor will be the first thing plus the second thing, and the second factor will be the first thing minus the second thing. And voila, we have factored our problem. We've factored our equation, our equation featured in the problem. Now we've got to solve this. And as we mentioned before, the fundamental theorem of algebra gives us some good insight. We have 4th degree. That means we should have 4 solutions to be on the lookout for. So we'll see if that ends up matching up. As far as what we have, we can break this apart a little bit further. That x squared minus 9 is going to be x plus 3, x minus 3, if we're so desiring breaking it up further on the page. And that first one, we did it a little bit like this on the first page. We can think of that as x squared minus a negative 9. and then treat again each one of these things as something squared minus something squared. So the question becomes, well, how do we get a minus a negative over there? And the answer is we use 3i. So this would factor into, by the way, as I'll just pop it over here, x plus 3i times x minus 3i. And voila, we have our equation completely factored, but we haven't solved the problem. Our last bit is to actually use the zero product property in order to determine the zeros themselves. In this case, they are negative 3i, positive 3i, negative 3, and 3. And you know, negative 3i, I've never seen a 3-year set of numbers. I don't know. I'm running out of gags here. I'm pretty tired. But there is our work here. So this was sort of a heavy-duty difference of squares, but there's definitely some stuff to deal with when we ended up with sort of imaginary pieces. But that's okay. The important thing is that we have the correct number of solutions to the equation, which we did in this case. Question number 3 is a 4-term polynomial, and as the strategy says up the top, or at least confirms, 4 terms suggest to us grouping. Now I should warn you that it's not going to be true every single time. You'll run into 4-term polynomials and attempt to do grouping and not end up with that. Oops, bumped a bunch of clipboards. You can run into a 4-term polynomial and not actually have the ability to break it apart in this way. But if we're giving this to you on an ESQ, we obviously want you to apply this technique. So what I'm going to do to kick this thing off is I'm going to treat it as 2 separate binomials. And this is very similar to what I did on, I believe, the first problem that we ran into. I'm going to split it right down the middle, and then I'm going to look for GCFs on each half. So this will be x squared times x plus 3. And on the second one, I see a minus 4, and that leaves me an x plus 3 as well. From here, as we mentioned earlier in the video, the 2x plus 3's are both a common factor, so we can GCF those out. And then we are left with whatever was sort of behind them, which is x squared minus 4. Now we're still intact here to satisfy the fundamental theorem of algebra because our degree is 3, and we have a squared polynomial and a linear polynomial. But in fact, this one factors so quickly and smoothly, I don't think it's necessary. We get x plus 3 times x plus 2 times x minus 2, the latter two coming from the difference of squares, which will give us negative 3, negative 2, and 2 as our 3 solutions, which is kind of cool. Like nothing wild, but nothing terrible either. So again, the 4 terms, I think that's really your key, is recognizing 4 terms points us toward factoring by grouping, and then of course just executing the technique, separating it apart, GCFing out appropriately, and then breaking things apart and solving with the correct sign. You know, sort of attention to detail at the end. And then finally, last but not least, we have question number 4. And question number 4, the strategy I put up there is GCF plus Diamond. I think the Diamond part sort of stands out the most when you look at this for the first time. You just go, oh yeah, there's 3 terms. I'm sure it's going to be quadratic somehow. But if you really inspect it, you'll notice that it's not. It's starting with an x to the 3rd power. That would be a problem, except there's an extra x with the first term, the second term, and the third term. And I just used the word extra, and I don't know if that's even an appropriate way to say it. Just that if there's an x in each of the terms, if there's some factor that's replicated each time, just GCF it out. Pull it out of there, get it out of the mess. Otherwise, if you leave it inside, it can start drama and just kind of cause this sort of internal hurricane. That's just a mess. So I'm going to go ahead and pull out that GCF of x that's here. And that's going to leave me with x times the quantity 2x squared minus x minus 15. And of course, it's still all equal to 0. So at this point, I'm going to focus my attention on the trinomial. This looks like a hard diamond problem. So that's exactly where I'm going to go here. We want to figure out what 2 numbers multiply to negative 30. So 2 times negative 15 is negative 30. And then add up to the leading coefficient in the center, which is negative 1. Now, those of you who are experienced in 3rd grade math probably recognize the pair that we're looking for here. We want negative 6 and positive 5. So what we end up with is on the outside, we still have that lonely x. I suppose people aren't probably bothered too much by a lonely x. But on the inside, we have 2x squared minus 6x plus 5x. Again, notice the minus 1x and the minus 6x plus 5x. Do you get it? Do you see what I'm saying? Yeah. So we got that, and then of course minus 15. So from here I do need to GCF this piece out. So just kind of being careful, I'm seeing 2x times x minus 3 plus 5 times x minus 3. And that's going to leave me with a GCF of x minus 3, a second factor of 2x plus 5. And then, of course, we had our original GCF. That GCF deserves to play as well. I want to say it deserves to be where the deer and the antelope play. I have no idea where that came from in my memory. Why do I know home, home on the range right now? I don't know. But what I do know is that was the final one of our problems. So you've gotten to see a little bit of all the factoring techniques. The only one that didn't appear in our video was MOP, but as I said, I don't know if that's going to appear on a standard quiz or an ESQ in your case. So I wouldn't stress about it. I think you've got what we need. So just as kind of a quick little reminder, we talked about the factoring strategies that were out there, sort of how to recognize them, and sort of did some examples, just kind of get them back in your head. And then we proceeded to go forward. The first one of our problems that we encountered looked like a quadratic. It smelled like a quadratic, but when you checked its license, it was actually 22 jump streeting us. This was a fake quadratic, but we did the diamond just like normal. We just had to be a little more cognizant in factoring. And of course, since the degree was 4, we wanted 4 solutions, which we got. In our second one, we had 2 terms, which pointed to a sum of difference of squares or cubes. But because of the even powerness of the whole thing, we instead had our classic difference of squares, which broke apart. We had some extra factoring at the very end to put together, but it wasn't problematic in any way. It wasn't difficult either, I don't think. Like, this was pretty doable for what it was. Yeah. So our third one, 4 terms, led us to factor by grouping. Again, not something that's going to translate into every problem you ever encounter, but here we're trying to practice the basic fundamental factoring skills, so it's probably going to be this strategy when it runs up later. And then last but not least, I thought a pretty clever last problem that someone wrote at some point that had us GCFing something out and then landing in a hard diamond problem. Both skills you have ample experience with, but that in particular here forced some attention to be paid. And speaking of forcing attention to be paid, I want to go to sleep, which I was going to try to make a joke of like forcing my attention to be paid to the dark ceiling. I don't know. But hopefully you got some really good instruction here. You got some good reminders and got some vocabulary and some factoring strategies back onto the tip of your tongue. And yeah, until we meet again, I hope you have a great time, and I hope you learned something or rekindled some once lost memories and education by watching this video. Thanks, everybody.